Extreme values and the first derivative test. It's so good. It's so good. This line of thinking is finally complete. Way back when, in advanced functions, it was, how do you find these max mins? You know, all we could do is just draw the shape. And it felt like actually the most important thing was missing in the graphs. You know, I tried to gloss over. It's like, it's okay. As long as we get the shape, it's okay. It's not okay. The max and min is everything. We got to know the max and the mins. We got to know them. Here's max mins. Together we call maximum and minimum. As a group, we call them together, we call them extreme values, since they represent the highest or the lowest, the most extreme values over a certain, that word used a little sloppily there, over a certain range, over a certain domain, over a certain interval would have been a great word. Interval. I like that the best word should have been in these notes. Over a certain interval, we're looking for the highest and the lowest values. Okay? The last phrase is italicized because we should note there are two kinds of extreme values, local and absolute. And before I explain them, just let me show you in a quick picture what I mean by local and absolute extreme values. Okay? Some crazy graph like this. And there's local ones. That's a max. It's a maximum in that particular interval. This one's a max. This one's a max. This one's a max. This one's a max. But there's only one absolute max. There's only one that's like, hey, the max, the max. And there might be a tie. There might be several of them. Like sine has many absolute maxes. And then minimums, min, local min, local min, local min, local min, but here, absolute min. It's also a local min, but it's the absolute minimum. One little thing to mention here is the absolute min doesn't need to be a local min, weirdly. The endpoints might be the absolute mins, even though they're not local mins. Weird in the phrasing of everything here. So managing the words here is maybe a bit of a situation when you first see this lesson. So local extreme values, I already explained it. Yeah, here's the fancy explanation, but I mean, I just explained what it was. A local extreme value is the max or min of a function in a certain neighborhood. They usually look like bumps or humps in the graph. These extreme values are not necessarily the highest point of the whole function. A local max is a max sufficiently close. You know, you just got to be close, and then you know it's the max in that little interval. Same with a minimum. You got to be sufficiently close. But absolute means no, this is bigger or tied at least with everything. Yeah, that's why it's greater than or equal to. It doesn't have to be higher than everything, but nothing can be higher than it. Is basically what that's saying. Is you can't have anything that's higher than that. Sine's the best example of this. Sine has many tops, and they're all absolute maximums because they all match up. Usually, we haven't played around with sine too much. Soon we'll see sine curves. We're used to sine curves that do this. You know, and hit the same maxes again and again. Soon we'll start talking about, you know, sine curves that die out like a little more real world here. That has dampening in there. You know what I mean? Okay, so anyways, for us now, sine's a great example to think about how you can have multiple absolute maximums. Let's jump ahead in our thinking. Well, no, we're not jumping ahead. Way back when I taught this course, I waited till now. I sort of left it as a surprise. I like the dramatic unveiling of these ideas. I don't like that anymore. I try and develop the idea as we're going so that when you get here, you're less than surprised. You already know what's coming. At a local max or min, the derivative is going to be 0. The slope of the tangent is going to be 0. I've tried to hammer away on that idea all the way through, right from the beginning of rate of change. You say, okay, yeah, well, there's one important point. There's all these tangent slopes, and they're all important somewhat. But this, where the tangent slope is 0, is really important because there's a potential max or min there. You're like, potential max? No. Derivative 0, you've got a max or a min there. Like, oh yeah? Well, just take a look at this guy for a second. Yeah? So that's why I'm saying potential. We just got to throw that in there. We'll have to check to make sure. We think when the derivative is 0, we're pretty sure we found a max or a min. How are we going to know? Don't worry, that's not going to be a big problem to find out. I got 2 ways to find out. Today's lesson, and then tomorrow afternoon's lesson, I got another way to find out. Tomorrow morning. You know what I mean. Later. So the procedure seems simple. If we want to find the max minimum values of a function, we just find the derivative and set it to 0. That is absolutely true. That's what we're going to do. We were just doing that. We were building those charts and we were finding maxes and mins. We can already do that. What about absolute extreme values? Absolute's a little tougher. Just a little bit tougher. Sadly, to find absolute, this is going to get highlighted. Because this is a test question that is usually perfect. Virtually everybody gets it perfect. And then there'll be a couple people that completely do it wrong because they don't understand one important thing. Sadly, to find absolute extreme values, we need to find all the extreme values and then compare them. It's going to be a little bit of work. I'll do an example today to see what you mean. You'll see what I mean by this. You got to find all the extreme values, and then you got to compare to see who's the absolute extreme. You got to like have a playoff sort of. You're like, okay, you guys are all the guys in the playoffs. Now let's find out who wins. And it's a bit of a pain. Yeah, I'll show you. We will then need to compare these extreme values with the end values to see if the max or min is at the end point. That's what I was referring to in that opening example. The absolute max might be one of the extreme values. We'll have to compare all these. The picture makes it look like you're going to have 100 to compare. No, in general, there will only be a handful to compare. But then you better check the endpoints because maybe the absolute max or min's at the extreme values. So these are all the guys that make the playoffs. Playoffs. These ones make the playoffs, and then you got to run the playoff to find out who wins. Yeah? You'll see. You see, there's a procedure, though. The good news is there's a procedure. Do this, then do this, then do this. And that's why most people get perfect on that question is I know the procedure. You just do these things. Well, especially as an assignment. Yeah, it's good. Yeah. It's going to work good. Where was I? What was that last part? Okay, I already explained it, but here's another picture of it. We got to find all the local max and mins, put them together with the endpoints, compare them all, and see who wins. The comparing is a pain, but it's not difficult to understand what we're doing. We're just going to sub the numbers in, find out who wins. Yeah? The following theorem should be obvious. Well, let's see if it's obvious. If f is continuous, and f has both an absolute max value and an absolute min. Oh, if f is continuous, then f will have an absolute max and an absolute min. You got some interval, there's got to be some highest and some lowest point. Okay? Not true on an open interval. Yeah, this is on a closed interval. On an open interval, the function could go forever, straight up like this, and you never do get an absolute max. But on a closed interval, if you say from here to here, we're going to be able to find an absolute max and an absolute min. Some new words, so I got to be careful here. Don't teach this too fast. Last thing before examples. Critical number. For a function, c is called a critical number if the derivative is 0 or if the derivative does not exist. So these are important numbers. And you might have started to find that out in the homework, is that once you've done the derivative, there's two things that will be important. One is the derivative 0? Well, we're going to want to know that. And second, we're going to know maybe the derivative doesn't exist. And both of those, we call them critical. Ooh, critical situation here. Zeros of the numerator and zeros of the denominator. Or negative square roots, like problems. A critical point, it's just the point where f prime is 0 or f prime doesn't exist. So instead of the x value, that's what this is. This will be the x value, and this is the point, x comma y. So the critical number is the x value of the critical point. These critical points could be extreme values. You're like, what could? How's it could? Well, that's what I was saying here. It could be an extreme value. Maybe the derivative goes to 0 and it doesn't turn. How are we going to know? The chart you were already building will tell you. It'll say positive derivative, negative derivative. Or maybe it'll say positive derivative, in which case you didn't actually get a max. You'll see in the examples. And finally, a stationary point. This is where the derivative equals 0. Anytime the derivative equals 0, you've got a stationary point. Oh, there's more words here. Oh, another word's coming up. An example, then more words. Okay? Any questions about these words, though? They're brand new words, but I hope the concepts are fairly Fairly straightforward. Oh, I'll put beside could be, so if you're rereading these notes, you know what I mean. Could be, I really tried to exaggerate, there's a derivative 0. That's not a max point. So just because it's derivative 0 doesn't mean you found a max. It's like, oh, this thing's in the playoffs now. You know, I think it is. I'm pretty sure it's a max. But I better check, and I'll show you how to check. Here you go. Find the absolute max and min. Here. Hey, this is the type of question that is not tricky. It'll be on the assignment. One like this. And there'll be no tricks. I'll give you a function and a domain and say go. You know, and you just got to know the steps. Here are the steps. Y prime. And this chapter loves questions like this with these scary fractions. You're like, oh no, here we go with the fractions. And the fractions are all set up very nicely so the derivative handles it easily. Derivative of 1/4 x to the power of 4 is x cubed. And I'm going to pause there for questions. Because that's either like, yes, that's so obvious to me, or it's like, where are you getting that from? But it is so nice if you just give it a second. But don't let me go on if there's a problem here. Is that clear? 4 comes down, 1/4 is waiting there. It's perfect relationship. 4 1/4, 4 times 1/4 is 1. So then, 2/3 x cubed, I get 2x squared. 2x squared. Whew. And then minus 5x minus 6. So be ready for homework questions like that, where it's like, it looks like scary fractions, but it's not. Questions on that derivative? Next step. We're looking for extreme values. I want maxes and mins. So our procedure is, I'm going to write out the words here to really help you when you're looking back at this later. For max mins, set y prime equal to 0. And if you're really with me and you're like, oh, wait a minute, what if they're not max or mins? Yeah, I'll get to that in just a second. To investigate, to find out our potentials, to find out our playoff performers, people that make it past the first round, you set y prime equal to 0. The x values I find here will be critical numbers. They'll be potential max mins. Probable. I'll say probable max mins. Okay, here comes the factoring, just in case the factoring's not right up to speed here. The whole procedure here, let p at x. -6 there, thank you. Whoa, look at that eraser I had there. -6. Small eraser, fix this up. -6, great catch, thank you. And you just try out some values. You say, okay, what's the potentials here? P at 1, and you sub that in. And P at 1 is 3, -2, -8. That doesn't work. P at -1. -1 plus 2 is 1. Plus 5 is 6. Ooh, is that 0? I think it's 0. Let me check it again. I've got a potential here. -1 plus 2 is 1. Plus 6 plus 5 is 6. Minus 6 is 0. I like it. You're probably pounding them into your calculator. That's fine. And therefore, what I've learned, if p at -1 is 0, I've learned that therefore x plus 1 is a factor. Ready for my synthetic division here? 1, 2, -5, -6. K value, -1. Bring down the 1, -1. Add, multiply, add. Okay, stop me now. More on synthetic division? Is it good? Is it good? With synthetic division, you write down the coefficients of p at x. 1, 2, -5, -6. You bring down the first one, and each time you come back up, you multiply. So 1 times -1 is -1, you add, times -1, and you add, times -1, you add. Now, you don't like this, you can go back to long division, but most people by the end of the long division section are like, tell me you got something else. Yeah? And this is, it's actually long division. It's just a short form of doing all that. So if after that explanation it's not enough to get the rust off it, that's maybe where you got to start. This lesson stuff is a quick video on synthetic division. I must have done a video on this synthetic division. Yeah? And you just go, okay, let me just get this down. Because it's not impossible, actually. It's not the worst thing ever. When you first see it, it's like, this is crazy, but it's not the worst. So what I get here then is, what was I doing? 0 equals, now I've got x plus 1, x squared plus x minus 6, x plus 1, now some easier factoring, x plus 3, x minus 2, should do it. And then an important sentence here, I'll switch colors here, important sentence for us. Last course in advanced functions, then we would have said, therefore, x equals -1, x equals -3, x equals 2. That's all true. But we got a little bit more information now. Therefore, the critical numbers are -1, -3, and 2. Subtle difference between that and advanced functions. There we were just finding zeros of a function. Now we're finding zeros of a derivative. Conclusion is slightly different. Okay, if your brain got distracted there, let's just rewind to what just happened. We took the derivative, we set it to 0, and now we've come up with these possibilities. These x values have put up their hand and said, me, I think I'm an extreme value. Can you check, please? Yeah? Because they might not be. And the chart is the perfect way. That's why the chart was such a big deal. The chart tells us exactly what's going on. So let me go through building the chart again, if the chart's a little rusty here. Here are the intervals. We want to look at x less than -3. We want to look between -3. Oh, hold on. Hold on. So excited to build the chart, and I will build a chart. But I just want to help you out a little bit on homework and on tests. This question doesn't actually ask me to say whether these are max or mins. It says, find the absolute max and mins. So I don't have to go through the whole chart thing. I don't need to know whether these are max or mins or not. I just need to know who wins. Who's the biggest of the big, who's the smallest of the small. And I've got these nominees. So what I'm going to do is I'm actually going to build a table, but it's a table of values. So for absolute max and min questions, you don't need to go through that other procedure. You can if you want. All you need here is who wins? Who's the highest? Is it -1? Is it -3? Is it 2? But there's 2 other x values in the playoffs. There's these 3. And then there's 2 more. Let me change to another picture to help you find the other x values that are in the playoffs. Snuck that in there. Does the picture show what the other x values that are in the playoffs? Okay. What are the other x values in the playoffs? Maddie. These ones are always in the playoffs. It might not even be a local max or min. Do you see why I don't care whether these are local max or mins or not? All I want to know is who's in the playoffs. Who could possibly be there? So here they are, the possibilities in the playoffs. I always put them in order, but it turns out you don't have to. I only realized that one time last year when someone in the calculus just put them in any old order here. But I always put them in order because there's other questions where maybe it sort of matters that you get them in the right order. So I'm just used to it. -5 is in the playoffs. -3, -1, 2, and 5. And when we do all this subbing, you might be like, well, why don't I just do all the x values then, as long as I'm going to do them all? I'm like, oh yeah? -4.99, -4.98, -4.97, -4.999. We actually have narrowed it down a lot. It may not feel like it. You're like, I still got to sub 5 in. I know, but you don't have to sub an infinite number of numbers between -5 and 5 in. So you have narrowed it down dramatically. And then it's a pain. You just got to sub these all into the original function with the fractions to find out all these individual things. Well, I'm going to do them all. Well, who is the one who made their calculator Emmett? Emmett can make his calculator do something, which I knew it could do, but I never really sat down to do it, where he just puts the function in and then just starts jamming x values in, right?
Yeah, so you just type it in with the x's.
He's gonna train us right here. So if you're into this, let me get the calculator up and let's just see. Hopefully my ROM version is good enough. Okay, Emmett, teach me. Menu 1, go. Just put in the original function. So, I'm guessing you want to be in math mode, yes? He says probably. Maybe he is, not sure. So anyways, here we go. 1, ABC. What's happening? 1. Oh, does it want the ABC first? Oh yeah, 1. That's funny. Why the Casio calculator you press the fraction first? Okay, it doesn't matter. 1 over 4, and you just do x's. X to the 4. Plus 2, 3, x exponent 3, not 33, 3. Then 5 halves. Okay, so minus 5 halves x squared minus 6x plus 4. Really important you check this before you start subbing x values in, right? 1/4 x fourth plus 2/3 x cubed minus 5 halves x squared minus 6. I got it right. Do I press equals? No. Hit execute, he says.
And then you can do whatever value you want. So you like -5.
Yeah. Hit -5.
And then the little arrow button under command.
Here?
Yeah.
Little arrow button under 10, he says. Hit that.
And then type X. And then execute.
I love this.
And then you can go back up with the arrows
Yeah.
to the first one, and then hit execute.
Okay, so let me totally explain what's going on. I get what the computer's thinking. Here's what you do. You enter in this thing. 1/4 x fourth plus 2/3 x cubed minus 5 x squared minus 6x plus 4. It comes back, and you press enter, and it says 4. And you're like, where are you getting 4 from? I haven't put anything in for x, so it assumes x is 0. And it gives me with x equals 0. And then I go, hold on. Put -5 in as x. Then go back and do it again. And when you do that, you get 533/12. Now, you can like that or not like that. I like the beauty of it. Geez, is it going to let me convert it now? No, it's not going to. So I'll get that as a decimal in a minute. And then you go -3 in for x. Go back up, yes? Hit it again. What did I get? 7/4? Go down. Just hit delete?
No. So you go up to the -1 to X,
Yeah.
and then here it says DL in screen.
Oh, yeah.
Yeah. And then DL and then L cancel line.
Oh, yeah.
And then F1.
He wants to tidy it up. Delete line? Yes. Oh, yeah. Yeah, yeah. Emmett's on this, eh? Which reminds me of first year, or sorry, not, by third year university, we used to do like homework. We'd always make sure there's a computer person there, and a math person there, and a physics person there when we were doing our homework. Because you never knew when you needed one of the people. Like all of a sudden you go, what is this talking about? I'll be doing my math homework. What is this talking about? Oh, well, that's the force. Da, 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 da. Oh, okay, thanks a lot. And then the physics person goes, I can't do this integral. And the math person goes, I can do the integral. Da, 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 boom. And then stuff like this, technology. It's always nice to have someone who knows the technology. Okay. X, -1. -1x, yes? -1 in for x. Enter. Now run the equation. 85/12. There's also another way to do this. I don't know if it's better than Emmett's way or not, but my brain is now, my old brain is starting to remember that there's another way to make this all happen. Up here, Delete the line? Yes. Get that out of the way. Now, 2 in for x. 2 in for x. Enter. Up to equation equals negative 26 thirds. Delete line. Yes. 5 in for x. Enter. Up here. 1813 over 12. Anyways, what was the game here? Maybe you're not interested in that at all. Maybe you're like, by the time I learn all that, maybe I could have typed it all in myself anyways. Hey, that's fine, you know, but this one's sort of a pain to sub into. The game was find out who is the winner. Is it 533 over 12? We're going to need these decimals to be able to compare them. 533 over 12, 44.4. I can do that one, 1.75. I can do this one, 7.08. 26 thirds, I can do that one, negative 8.33. And what was the last one? 1813 over 12? 1813 divided by 12. 151. Ooh. There he is. Absolute max. And then absolute min was the negative 8.33. Will. $8.67 there? Oh, yeah. Thank you. Trying to ward off Alzheimer's by doing them in my head there. And everybody always asks me during this lesson if I name my son Max because of this lesson. And I always used to say no. And now I go, I hope not. Yeah, but I guess I'm not sure. I was teaching a data management class in summer school one year, and they're like, my kids were Max and Bella. I'm like, well, probably not. I mean, Max and I didn't Bella, and we were studying normal curves in data management. They're called bell curves. They're like, bell curves, Bella. I'm like, oh no, I'm naming all my kids after this is little calculus Todd and her little brother algebra. Okay, I know the subbing went out of hand there. But hopefully up to the point I started subbing, you're like, pretty straightforward. Derivative 0, sub them all in. And some questions the subbing's crazy and sometimes the subbing's not crazy. But I did a crazy subbing once, so if you ran into crazy subbing, you knew what to do. Questions about absolute max and min. Simon. It didn't even give you what? When you pressed enter, it gave you the answer. In its memory, it already had x equal to 5. Mine already had in its memory x equals 0. So that's why I got a different answer. So somebody, maybe you, maybe whoever had the calculator last, had already put x equals 5 in the memory. Your calculator right now thinks x equals 5. It doesn't affect anything until you actually put one of these things in. So it did the first sub for you with x equals 5. Weird, right? Other questions? If that part of it, you're like, no, computers, programming, that kind of stuff, not my thing. I'll just sub them all in. Thank you very much. Totally allowed. Yeah? Okay, some questions for discussions. Do stationary points always result in local max or mins? No. Keep hammering away on this idea. I'll just draw this picture and I'll say no. We can get y prime equal to 0 and not end up with a max or a min. It really depends on the categorization of these things, which I didn't do in that question. Actually, we didn't really categorize these. We could figure it out from looking at the values, but we really didn't say whether they were all max or mins because we didn't care. All we wanted was the absolute max and mins. You say, well, what happens if we have to categorize them? Yeah, I know. There's more examples coming where you have to categorize. Are all critical points stationary points? No. You could have somewhere where the derivative doesn't exist. It's a critical point, but the derivative doesn't equal 0. And there's plenty of other examples of situations that come up where just because it's a critical point, just because the derivative doesn't exist, doesn't mean you've got a point where the derivative equals 0. Yeah? So slight nitpicking at the definitions there, but just want to mention those things because they do come up in the second half of this course where it's like, oh, whoa, 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 that's a stationary point. Whoa, whoa, no, that's a critical point, but it's not a stationary point. You know, but we're not beating that to death too much in this lesson. So here's officially the first derivative test. The reason this thing is called the first derivative test, and yes, there is a lesson coming up called the second derivative test, and that's why we label this lesson like this. But for now, the first derivative test basically says this. If you go from increasing to decreasing, you got a max. You go from decreasing to increasing, you got a min. That's what the first derivative test is. Here it is in fancy words. If f prime changes from negative to positive, then we found a local min. If f prime changes from positive to negative, you got a local max. And if it does not change, it's neither a max or a min. See? Like this. Maybe it's not going to change. How will we know? Yeah, it's coming. I'm going to finish the lesson. That's what I'm going to do. Questions there? Determine the coordinates of a local extreme. And I'm going to add a couple of words in there that's usually in the homework. Determine the coordinates of all local extreme and categorize them. And categorize means say what it is. Say whether it's a max or min. And as you're doing this, that's sort of implied in the question anyways, but it doesn't really say the words. You'll see what I mean as I go through it. Is this a different function than the last one? Even though it sort of looks like it might be the same? Okay, so same procedure. I'm going to do a lot of the algebra, and then I want to pause for questions at certain times, okay? So, y equals blah, blah, blah. It says local extrema, which means max and min. And that tells me find the derivative. So y prime equals x cubed plus 5x squared plus 3x minus 9. Again, another one of those questions that really looks like it's going to be crazy fractions, but it's really not. And this time, we're not going to have to sub into this thing, and you'll see why in just a second. So we don't ever have to worry about the fractions too much. So that line I did in red. For max min set y prime equal to 0. And maybe I should have put for potential max min. You know, maybe they're going to be max mins. But you're going to see how we decide in just a minute. Set y prime equal to 0. Here, we're getting some x values to put in the playoffs to figure out whether they're max mins. So I go 0 equals x cubed plus 5x squared plus 3x minus 9. Let p at x equal x cubed plus 5x squared plus 3x minus 9. P at 1 equals 1, 6, 9. Oh, 0. Look at that. And if 1 doesn't work, you try negative 1. You try 2. You try negative 2. You try 3. Ooh, little shortcut here. Don't try 2. The only numbers that are going to work are the ones that divide into that last thing there. That's the only way this can work out. Try 1, try 2. You try 2s, they just won't work, but there's a little shortcut there. Therefore, x minus 1 is a factor. So I use k equals 1, and I do the satanic division here. 1, 1, 6, 6, 9, 9, 0. Happy to see the 0 down there. That tells me, yes, it's going to work out. That's what factor theorem's all about. If I get a 0 when I sub in 1, that means when I divide by x minus 1, I'm going to get remainder 0. So we have x minus 1 times x squared plus 6x plus 9 equals 0. Two things that multiply to 9 and add to 6. Three and 3. So I get x minus 1. And so, and then, oh, I changed colors for, it's not too dramatic when I change colors and just keep changing colors. I really meant to just change colors for that line. So let me go back and highlight that line. Not because it's that difficult, really, but because it's so darn important. If you want max mins, set the derivative equal to 0. I'm going to keep saying that So many times in this chapter. And then when I get to here, I will change colors and try to stay on that new color, stay off that new color. Therefore, the critical numbers are 1 and negative 3. Okay, but this time it asked me to categorize them. It asked me to say what they were, whether they're max or mins. And I'm going to say whether they're max or mins. A table of values could be used to do that, but it's not the most optimum way to categorize. Categorize, we want the other kind of table, which is, we're going to go x less than negative 3, between negative 3 and 1, and greater than 1. And if in the last lesson you were sort of blown away by the building of these tables, well, now I'm doing it live, so you get to see the whole thing. Here's y prime. I encourage you, let me just put a little highlighter on that y prime there. I encourage you when you're building these tables to write down what kind of table it is. It's a derivative chart this time, and that means the conclusions are different. And we won't really see until quad 2 why that's such a big deal. Because what we're going to do is we're going to go back to graphing, and we're going to have a y chart and a y prime chart. And there's different conclusions off each one. For you physics people, a displacement graph is different than a velocity graph, you know. And so I get x minus 1 times x plus 3 squared. And then I look in each category, I pick a value that's going to sort of be my tester. A number less than negative 3, I'll use negative 5. Between negative 3 and 1, I'll use 0, because 0 is so darn easy to sub in. And x greater than 1, I'll use like a 10, because big numbers are also easy to sub in when we're doing this kind of thinking. So my nominee of negative 5, if I subtract 1, I get a negative. If I add 3 and then square it, I get a positive. So it's going to be negative in here. Between negative 3 and 1, I get 0. So I'll get a negative and a positive, which means it's negative in here. And then over here, I get positive and positive, which is positive. But I want to stop for questions there, because the tables are really important. And if building that table is still a problem for you, now's a great time to frown or shake your head or let me know, because I want to explain it more if tables are a problem. So here it comes. How are tables for you? Building these tables. Nodding. Anybody having trouble with tables? No. Okay. So we've done these many times before, but with a y prime, here's this morning's lesson. This morning's lesson said, okay, that means it's decreasing, then it's decreasing, and then it's increasing. Remember, we're looking for max and mins here. If it goes from decreasing before negative 3 and then it's decreasing after negative 3, that's not a max or min. It must have done something like this. Decreasing, then more decreasing. That's important to know. But here it went increasing to decreasing. And what happens when we're increasing? Sorry, it went from decreasing to increasing. What happens when you go decreasing to increasing? Minimum. So right here, there's a minimum at 1 comma, it said determine the coordinates. 1 comma, how do I get the y value to go with this? Yeah, just put in 1 into this giant monstrosity and get the y value that goes with it. Only one sub to do here, so I won't use the fancy calculator steps here. I'll just go in and go 1/4 times 1, yeah, plus, oh, it's 1 we're subbing in. What a nice sub. See? 1, 1, 1, 1. I'm just adding these fractions. Okay, 1/4 plus 5/3. See, my calculator, I have to press it first. That on-screen calculator is so awful. 3 halves minus 9 plus 7. I get 17/12. Roop says yes, 17/12. Can you see the difference between the two questions? With absolute max and mins, we've got to check each point to see its y value. Here, when we're categorizing max and mins, we just need to know whether it is a max or min. But they wanted the coordinates here, so I was stuck with the subbing. It's a matter of knowing when to sub and so on. What questions do you have about this one? more time? Ooh. Some other derivatives coming up here. F at x equals e to the negative x squared. I'm just doing the same thing on this. So f prime at x equals e to the negative x squared times negative 2x. And I'm going to keep going. And if you've got a question on that, I'll come back in just a second, because it could be you haven't even got to E homework yet. And so maybe we need to talk about that. But take that as read for a second. Say, okay, very good chance Mr. Todd's right about that. I'll do the rest of it, and then I'll come back to the derivative. You have some time to think about it, and think about whether that derivative you have questions on. So, oh yeah, other color here. For max min, set f prime equal to 0. We're just going to keep saying that over and over again. That's the whole plan for finding max mins. Set derivative to 0. I get 0 equals e to the negative x squared times negative 2x. And then we do have to talk about something very important here. I'm going to get the red highlighter ready, because what I'm going to write next is very important. I'm going to write never equal 0, and then I need some help. Somebody needs to help me with that, to tell me how is it I can just look at that and know that thing never comes out to 0. No algebra, although the algebra, you could use algebra, but there's something about this situation that tells me no way that equals 0. And over here, I get x equals 0. How do I know? What is it about e to the negative x squared, or e to the anything, that I know for sure? I don't have to worry about that part at all. It's nice when you're doing these questions. When e pops in, you're like, oh, that's going to make some of the algebra a little easier, because I know e never comes out to 0. What is it about e? Well, e to the x, or e to the anything, that says never equals 0. Sal? Yeah. I like the way he's explained it. He's used one way to say you can't take anything, e to the, and multiply it by itself some number of times and come out to 0, no matter what. There's going to be a number here. This is going to be a number. It's not going to be 0. Anyone have a different explanation? Not better or worse. There might be a different way to understand this. Yeah, when you think about e to the x, and still after all these years, I immediately think about this. Now, it might be stretched or compressed or whatever like that. There's lots you can do, but in the end, it never equals 0. None of those exponential functions ever equal 0. They can approach 0. They get really close, but they never equal 0. Oh, what if I forget, Mr. Todd? What happens if I go after this thing and I believe that e to the negative x squared is equal to 0? I'm like, okay, let's try and solve it then. Yeah. When you move e to the power of over to this side, it becomes ln. And so I'm doing ln of 0, and if you type ln of 0 in your calculator will let you know. It's not going to happen. You can't get ln 0. You can't calculate ln 0. And why is that graphically? Well, ln looks like the log graphs look like that. You can't punch in 0 to those things. It's like punching in a negative to a square root. You just can't do it. And so then you'd get no answers there. So you don't have to memorize the e's never equals 0. It's just really convenient because it saves you some algebra. Now I'm ready for my chart. X less than 0, x greater than 0, f prime, which is e to the negative x squared, times 2x. My points, I'm going to use negative 5 and positive 5 as my test points. And when I sub those in, e to the negative x squared is always positive. This will be negative, so I get negative. And then I get positive and positive, which is positive, decreasing to increasing. So if it's decreasing for x less than 0, it's increasing for x greater than 0, what's happening at x equals 0? That's a minimum. Right there. Minimum at 0, comma, blank, and then we're going to go back and see if the derivative's okay, because the derivative might not be okay. Will? Hold on. My mistake's right here. That's a negative 2x. I didn't write negative 2x when I went right there. And so now I've got a bunch of fixing to do. A bunch of fixing. Oh my goodness. Positive, 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 negative, negative, increasing, decreasing, and it's a max at 0, comma, well, e to the negative 0 is e to the 0 is 1. Thank you all. Procedure the same, derivative different. So let's go back to the derivative. The derivative of e to the x, e to the anything, is e to the anything. The first step of the e derivative is the easiest derivative we've seen so far. You just write it back down again. The only thing you got to watch out for is chain rule, which is the derivative of the exponent, and here the derivative of the exponent is negative 2x. Any questions about that example? It's harder because there's more to know, but it's easier because there's a lot less algebra. More time? How many more? Oh, one more example, and then a final thought. The final thought, pretty easy, I think. And then word problems. I know you're excited. Tomorrow's word problems. Yay! If you're looking them over, just know that there's only so many types of word problems. When I'm doing them tomorrow, it's going to be a complete freak out. And then when you go to the homework, you're like, oh, this is just like the one you did in class. Oh, this one's just like, and there's these different types. And you just got to learn to categorize the types. So it'll seem bad when it's happening, for sure. We're finding extreme values of rational functions. First step, derivative. And hopefully this derivative doesn't scare you after everything you've been doing. Derivative of the top times the bottom. Minus derivative of the bottom times top all over the bottom squared. Just going to get that door, and then I will check that to see if I've made any little clerical errors there. Derivative of the top times the bottom. Minus derivative of the bottom times top. All of the bottom squared. Beautiful. Okay, sometimes the easiest factoring questions are by far the most difficult because we don't do many of the easy ones. It's always some crazy mess for factoring. And this is the easiest factoring in the numerator there is, except there's so few of them in the homework. It's easy to not have this under control. What kind of factoring will deal with this numerator situation? Simon. Yeah, it's just common factor. Yeah, it's weird how that one just disappears because you do it the first day of factoring in grade 10, and they're like, okay, forget about common factoring. And you sort of forget about it. But lots of questions just come down to a nice little common factor like that. And why was common factoring so important all the way through that homework, and why was it difficult to know when to stop when that answer right there looks perfectly good? It's not ready for today's lesson. It's not ready for finding zeros. And finding zeros of this thing now pretty straightforward. So finding zeros of this thing pretty straightforward. Critical numbers are 0 and -2. Well, I got to check the denominator to make sure to see if the denominator equals 0, because it can happen the denominator equals 0, and I got to include it in my chart. I'm going to add one more tool to your bag of tricks. You can do quadratic formula on this thing. It doesn't factor. You can do quadratic formula thing on this thing, and that's fine. But way back in grade 10 and 11, sometimes they talk about this thing called the discriminant. And the discriminant is a nice test to see if I even have to worry about this thing to do the quadratic formula. It does part of the quadratic formula without doing the whole thing, and allows you to go, do I even bother? And I got to tell you, as I was writing up here, one of the reasons I'm really bad for getting distracted while I'm doing lessons. One of the reasons I make little mistakes up here lots of times, because I'm busy staring at this thing going, oh, what am I going to say about this thing? Is it quadratic formula? And in my head, I immediately go b squared minus 4ac, and in my head, I get negative. I'm like, oh, it's not going to be a problem. It's not going to have any, because I just did the b squared minus 4ac. And the lessons on discriminant back then were just trying to tell you that, but they wrapped it up with so many conclusions and so on, and made it so weird that they didn't sort of build this tool into you, which is just to go, let's just give this a little b squared minus 4ac check here, grab the part of the quadratic formula, and if I do that, I get 4 minus 8, I get -4, and then no zeros. You see how that's nicer than going negative b plus or minus square, and doing all the steps and getting all the numbers to find out it's square root of negative. You can just test it out right there. I think you'll find a lot of the homework in this chapter doesn't drop you into derivative, not existing problems. They try and avoid that mostly because it's not really what the procedure is about. So I've really got two critical numbers. If I had got zeros in the denominator, I would have included those too. So I'm going to put an arrow up here as if, ooh, those got to be included too, but I didn't have any here. Questions? So here's my table. I need x less than 0. I need between, no, that's the wrong way around. I need x less than -2. I between -2 and 0, and I need x greater than 2. I'll pick my nominees out while I'm up there. My test values, I'm going to use -5. No, I'm not going to use test values this time. There's a way to do this without actually picking the specific test values, and maybe you like that better. You want to use test values? You go ahead and do it. In the numerator, I have -x, x plus 2, and in the denominator I have x squared plus 2x plus 2 squared. So a number less than -2, which means it's negative. So on the numerator, I'm going to get negative, and if it's less than -2, that's still going to be negative. The bottom's going to be positive, and I get negative. Now, I did that fast on purpose. Not to confuse you, but to let you know that building these tables doesn't have to take forever once you get used to the idea of I'm subbing in this type of number. Let me slow the next one down. Between -2 and 0, well, it's just easy to use -1, but I'm thinking of a number between -2 and 0. Negative's still going to be negative. X, well, I'm thinking of a number between -2 and 0. That's going to be negative. But when I add 2 to a number between -2 and 0, I'm going to get positive. The bottom's always positive because it's squared, and I get positive here. And then greater than 2, negative, positive, 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 negative. You can get that good. That's not because I'm 1,000 years old and done a million of these. That's not why I can do that fast. Once you've done a few of the tables, it's like boom, 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 boom. That should go pretty fast. Let me just highlight the conclusions there, because all those negatives and positives might confuse the issue here. Basically, though, what I've got is decreasing, then increasing, then decreasing. One more time, this conclusion from this lesson. If I go from decreasing to increasing, that's a minimum. So there's a minimum at -2 comma something. I'll get that in a minute. That's not a problem. And then there's a maximum at I wrote greater than 2 there. I was thinking greater than 0 the whole time, but that's a greater than 0 up there. Negative, positive, positive, positive. Yeah, okay. Maximum at 0 comma. Ooh, let me sub that in right now. Yeah, there's a nice sub. You know, subbing in 0 is always fun. Just ignore all the x's. Subbing in -2. Let's see if I can do it in my head. No, I'll get someone to check. -2. Oh, that's not so bad. -1. -2. 4. 0. 2. Oh, -1/2. Isn't that weird? Very symmetrical there. Okay. -2. -1. 4. -4. 0. 2. Yeah. Yeah, I think it's right. We're almost back to graphing again. We're going to go back and do all the same graphing we did in rational functions in advanced functions, except now we'll be able to find those max and mins, no problem. And some other stuff, no problem. What questions do you have about this example? Simon? You can handle this any way you want. Whatever it takes to think that through. Is that what you're asking? Do I have to? Oh, no, not in this case because it's squared, right? So I don't have to think too much about whatever this is, it's getting squared, so it's always positive. But if there were separate factors, you might have to think of the separate factors, yes. But this one was nice because the whole bottom was squared, so I knew it's always going to be positive. And I did this thinking to go, well, it's never going to be 0, so I don't have to worry about that either, you know. You can see how, as simple as the procedure is, let's just go over the procedure. Let's go over what calculus says about this. Take the derivative and find out when it's positive and negative. Yeah? Pretty simple calculus procedure. But all the little algebraic steps, which even 2 days ago, I'm listening, looking over people's shoulders, listening to the mistakes people are coming up to me with. 2 days ago, the algebraic mistakes you were making, I was like, oh boy. You know, like just little things that are like, and then 2 days later, all of a sudden it's like, oh no, we're not dropping the negatives so much, we're not missing the 2's, the x's, you know, your algebraic skills fly in this area. So if you've been frustrated, just stay a little longer and you might find that, hey, I'm getting better at this. It's going good now. Yeah. Other questions about this one? More time? More time? I don't think the last one's an example, it's just a thought. One final thought. Let me read the non-fancy version first. The non-fancy version says, if a function decreases up to a certain point and then increases after that, you found the absolute minimum. You don't have to go looking anymore. If you decrease all the way and then increase all the way after, you don't have to do any special research. You know that's the absolute max. And vice versa. If something increases the whole time, then hits some x value, and then decreases the whole time after that, that thing has to be the absolute max. There's no way for it to come back and beat it. That's what this says. If f prime is negative for all x before a certain value, and f prime is positive for all x after that value, you found the absolute max. If f prime is positive, or sorry, absolute min for that one. If f prime is positive for all x less than c, and then f prime is negative for all x greater than c, then you found the absolute max.